Hello and welcome to this tutorial on multiple linear regression from Analytics School Online. Well, as we know, we've covered simple linear regression. Let us try to know something more, dive a little deeper into regression. Now basically regression is of many kinds and each and individual regression model has different properties and different applications in real world. Well, like there are some regression models one of which we've already studied, like simple linear regression. Then there comes multiple linear regression, and as the name suggests, multiple linear regression is basically multiple features, multiple independent variables. But then there are also other forms of regression, which is polynomial regression, where our independent variables are different as well as they are raised to the power of an integer, which better defines some data sets and their regression models. Then there comes logistic regression and support vector regression. Well, these are some kind of classifiers which actually divide our data into certain parts and eventually tell us that these kinds of data or these data points are different from these data points. And let me tell you, this is not it. There are many more regression models, but these, as I consider, are some of the most important ones. So we shall only focus on these for now. And there are further videos coming up on different various regression models. There are also some regression models like random forest and decision tree models, which are good classifier models based on regression. But presently, let's focus on multiple linear regression. And so, what is multiple linear regression? Now, multiple linear regression is a multivariate statistical technique. As the name suggests, multivariate. Now, multivariate is basically the variables are multiple. There are two or more variables, unlike in simple linear regression. Like in simple linear regression, we had just one independent variable. Our equation was y0 equals b0 plus b1x. In multiple variable or in multivariate linear regression, we have two or more numbers of independent variables. So we have x1, x2 and like that up to n. What does multiple linear regression do? It examines and defines the linear correlation between two or more independent variables. So it actually defines the relationship between two or more independent variables and their corresponding single dependent variable, which we've always tried to predict. And finally, this is a little advanced knowledge to have presently, but once you start reading about machine learning algorithms, you would know that there are two classes of learning algorithms. One is supervised and one is unsupervised. So multiple linear regression or even simple linear regression are supervised learning algorithms, where you actually give some data set or a little data beforehand to your algorithm or to your model, by which the model gets trained. The model trains itself on the basis of that data set that you've given, and then further it uses more data to predict values of y. So basically it is supervised, like there is something which you need to provide first and then your model works. But in unsupervised learning, the other part, the counterpart of this, the algorithm is defined in such a way that you put data inside the algorithm and the algorithm will automatically define what kind of data it is, what it needs to do and how it needs to do. So those are the two types of machine learning algorithms, but don't worry, we'll study about them later. So moving on. Let's start with why we want to learn multiple linear regression. Now, in real life scenarios, we are going to come across data sets which are not simple linear regression models, which cannot be defined by simple linear regression models, because in practical scenarios, as we observed, there are many factors which are actually influencing a particular quantity. The value of that quantity is not solely based on a single other quantity. It is a combination of different kinds of other variables that define the value of the dependent variable. So to achieve better insights in our data, we must always try to include as many variables as possible, keeping in mind that they are significant, and then work with data. So multiple linear regression comes into play. And also there are some times when we try to use our common sense, reject some of the variables which actually should not have been rejected, but because we think in a certain way, our mindset is defined in a certain way, we try to eliminate those when we should not have actually done so. But with multiple linear regression, we can simply test the parameters and get those values. A multiple linear regression is also used to improve the efficiency and accuracy of our model compared to simple linear regression model, where we are actually only considering one factor, and now here we are considering more factors. And finally, how do we do it? Well, it's the same like last time. We are using the method of least squares. Now, for those of you who do not understand the method of least squares algorithm or are not acquainted with it, please go check out the OLS video, the ordinary least squares algorithm video, which is already there in this playlist. And you can simply understand the backend algorithm that is working or that is coming into play to implement the multiple linear regression model. I'll give you a brief revision of this for those who have already seen the video, but it's been a long time since then. Finally, we are going to fit a regression line to the available data and derive a model to predict values. That is our ultimate aim. And just to give you a brief revision of the method of least squares, in the method of least squares, what we try to do is that we assume, by using trial and error method, we assume a model which we randomly assign, and with respect to that model we try to calculate the residual values. Now, what is the residual value? As the formula given here, the residual value is basically the sum of squares of the difference between the observed value and the predicted value of a particular data point. Once we subtract these values from their observed point and their predicted point and we sum these all up, we get the sum of residuals, and our aim in method of least squares is to basically minimize the sum of these residuals. That was it for the revision part. Let's move further. Now, this is our characteristic equation of the multiple linear regression model. Now, this is one of the most important parts which you must consider to understand in depth, because this is what is actually going to give you a greater insight into understanding the model so that you can implement these algorithms in the future. So, the model as usual has 5 parts. The first part is the random error, which, as we know from our simple linear regression model, is the random term in the observations, the error term in the observations, individual observations. And the next part is our dependent variable y. The dependent variable y is the value which we need to predict or estimate, which we are going to predict or estimate using this equation. Then comes b naught or beta naught, whatever you might call it. It is actually the intercept parameter of the model. It is a constant contribution to the model. The value of b naught does not change or is not affected by change in the value of any independent variables. And finally, the two of the most important parts of this model, the set of coefficients, or as you say b1, b2, b3. Now you can call it b1 or beta 1, it's all the same. What it actually means is that this is the set of coefficients of the independent variables. Now, what does these coefficients signify? The coefficients are actually the impact parameters, the values that define the impact of a particular variable on the whole model. For example, if the value of b1, let's assume it to be 4, so on a unit change of x, there will be a variation of 4 units in the value of y, if everything else is kept constant, obviously. So if everything else is kept constant and the value of b1 is 4, so there is going to be a variation of 4 once you change the x1 independent variable by 1 unit. And similarly, that is applicable to all coefficients, and basically they tell us what are the variations in y once there is a variation in x. It's simple, isn't it? Next, x1, x2, x3 up till xn are set of our independent variables. These are our predictors or quantities that help us predict the value of y, and it's similar to simple linear regression model. It's just that there is a slight change. We've increased the number of independent variables, and that's it. Moving on further, presently we've just scraped the surface of the earth when we have talked about multiple linear regression. Let's try to dive deep into it and get to the core of it. Now, beta, as we know, is our coefficient parameter. Now, what is the range of beta? What does it actually implement in our data? The range of beta is simple. It's R, basically. It's the real numbers range. It can be positive or negative, but then there is a catch. The catch is that the value of beta does not actually in real life scenarios cross like 2-digit numbers. Like, for example, the range of beta would mostly be found between -5 to +5, because we generally scale our data, and if you are thinking what is scaling. Scaling is actually a data pre-processing part where we actually adjust our data values simultaneously so that when we calculate parameters, these parameters are not affected by the conversion between the x and y variables. So data pre-processing is a very important part in regression or in any form of model creation for machine learning or data analytics. We must always keep in mind that the better we pre-process our data, the better analysis we can do on our data set. Finally, x's define our features, epsilon represents the error, and y is our estimated prediction, and that's all. Moving on, this is the fun part, the visualization part, where we actually get to know what we are actually doing, and it's basically visualizing the model in itself. And now let me tell you that it's very difficult to visualize models when the number of independent variables are more than 3 or 4, because it actually cannot be plotted really well, and you need a little advanced libraries like matplotlib for Python and MATLAB softwares, which actually make your visualization very precise and give you a better visual model. But presently we are only going to consider models with 2 to 3 independent variables. So it is comparatively easy to visualize 2 to 3 variables, where it actually, instead of line in a 2D or in a simple linear regression model, here we have a hyperplane which divides the data points into 2 different parts. So just like in the simple linear regression model, we were actually creating a line, or our model was basically a line equation. In multiple linear regression, our model is basically a hyperplane, a plane which actually cuts the cube, this cube formed by 3 independent variables of pedigree, age, and BMI, which is actually trying to predict if a person is healthy or has diabetes. So what the hyperplane does is that it cuts this cube in a particular way, in a particular fashion, that it divides our data points randomly in between the cube, and when we input a new data corresponding to BMI, age, and pedigree, the hyperplane actually predicts if this is a healthy or a infected patient, and that's what a regression does. It basically gives you the idea and it classifies both of them. Now moving further, and I simply love this image. This is my favorite cartoon character, and the way he's looking at it, it's so adorable. Anyway, moving on. Finally, this is a better visualization of our multiple linear regression model. This is the hyperplane which we were calling in the last slide. So this is how you can differ between multiple and simple linear regression. These points lying below the plane are basically of a particular class, and these points lying above the plane are of another class. And once you input the values of grade, age, and sex, you will get a value of x here or here or here, or whatever you put your values into, and then there is going to be a judgment or decision in how your data is going to be divided. Finally, this is not for people who are just interested in creating the model. If you want to learn a little deeper into how regression models work, this is what I'm trying to share with you. Now, it is easy to actually implement a simple linear regression model with less number of data points on paper or offline, but when you try to implement large data sets in simple linear regression, you know how the calculations are done, but you need a computer for it. But in the case of multiple linear regression, it is really difficult to actually create the model on paper and find out the parameters if they increase more than 2 or 3. So we must learn, or we must understand, how the computer processes this equation and finds out the values. So the answer is matrices. Yes, matrices solving in computer processors or in computers memory is really quick. They are very efficient in calculating the matrix parameters, and there are very advanced libraries which help to calculate matrices very quickly, and they are very efficient. So what the computer does is that it puts your equation in different matrices. For example, these are the values of y, the observed values of y that we give in our data set. So this is the column of your data set which actually consists of the dependent variable. Then this is actually when you multiply these two matrices, you are going to get the value beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3 for each and individual observations. So for those of you who are acquainted with matrices and matrix multiplication, you can simply see here that this row is going to be multiplied with this column every single iteration. For example, this is going to be like 1 into beta naught plus x11 into beta 1 plus x12 into beta 2. So these are the beta parameters or our coefficients of independent variables, and when you add the errors you basically get your characteristic equation of the multiple linear regression model. And finally, this is how the computer does it, and this is how the computer calculates the value of beta. So after solving these matrices in a particular fashion, how we do it, we actually get these equations in the end, and these equations are what the computer solves to finally get the matrix of beta as beta cap, the estimated or predicted values of beta, which when put into the equation of y cap equals x into beta cap gives you the characteristic equation model, and this is the predictor model or the estimation model. And these are simply the matrices of beta and epsilon naught, and I guess we can move further. Just a small thing to notice right here. In our characteristic equation model there were only x1, x2, x3 till xn and so on, but here we are seeing a 1. Well, that's because we've tried to actually make it easier for our computer to understand. With beta naught or with the intercept parameter, we've actually multiplied 1 at every stage. Well, that keeps it beta naught, but just by adding a constant value we can actually make it easier for the matrix model to multiply with each and every other matrix, and that solves the matrices problem. Moving on. What are the tests that analyze the strength of the model? Now, simple linear regression was actually, as its name suggests, very simple. So we did not need many parameters to estimate the model. We were simply satisfied with a few parameters and we could easily understand that the model is good or bad in a certain way. But for multiple linear regression, it is a bit complex and complicated, because here you have to calculate a lot of parameters. You have to constantly keep an eye on the t-stat, on the p-value, on the standard error, on the adjusted r-square and the multiple r-squared. As I mentioned in the video of simple linear regression, r-square is basically not a good parameter while judging multiple linear regressions, because it always increases with the increasing number of independent variables, no matter how significant they are. So in multiple linear regression model, we've generally tried to efficiently use the adjusted r-square parameter, and based on this parameter we'll judge our model, and keeping in mind the p-value, which actually gives us a barrier mark for our significance level. We'll learn all these in the Excel implementation of the model, so don't worry if you're not getting it right. Just keep in mind that adjusted r-square is very important. It's the best choice for estimating the multiple linear regression model, and other values, p-value analysis is also important, and we'll look at their implementations in the coming video. Now, we were not facing many challenges when we were actually trying to implement the simple linear regression, but it was actually very easy, so we did not face challenges. But once the number of independent variable increases, we start facing three problems, and these three problems are, as mentioned, the elimination of multi-collinearity. Now I'll explain the term multi-collinearity in the next slide, but just for reference sake, multi-collinearity is basically the existence of a collinearity or a relationship between our independent variables, and it's not good. So moving on, we also need to avoid the overfitting of the model problem. Now overfitting of the model is, as the name suggests, overfitting, like increasing the number of independent variables again and again, and adding too many variables which actually do not need to be added or which are not significant in creating a better model. So we need to keep an eye on that too. And finally, the dummy variable trap. Well, actually it's not so important, as is the case, because we might not always have categorical variables. This problem is specific to having a categorical variable in our data set. Once we have this categorical variable, we need to make a small transformation in our data set and then apply it to the regression model, and we'll talk about dummy variable trap. So moving on, now let's talk about multi-collinearity. This is comparatively an easy concept, so let's learn it quick and efficiently. Well, this is the ideal case. As you can see, y is our dependent variable, x1, x2 and x3 being our independent variables. So what is zero collinearity? Zero collinearity is basically, as we can see, there is no relation or no intersection between x1, x2 and x3. They are completely independent. They hold no relation between each other. Then we come to the practical case, the case which we are most likely to find in most of our data sets which we get to analyze in real life. So these data sets are going to have slight collinearity, like there is going to be some values or some linear relationship between these independent variables. They are going to harm our model a little, but not so much. But then there is the undesirable case, the case of high collinearity, where our independent variables are highly correlated, and in between themselves they create a scenario where they try to project, or where they try to show false relationship, or it actually makes the model stupid, because if all your independent variables are related, you might as well just have taken one independent variable instead of adding so many other variables, and thus simply overfitting the model again and again. Now, how do you solve this problem of multicollinearity? We look at these solutions in greater depth, but let me just give you a brief idea. There are three ways which you can solve this problem. Well, there are many ways, but just focusing on what's really important right now, it's backward elimination. Now, as the name suggests, backward elimination is a process where you actually add all the variables, all the independent variables at once in your data set, and then start eliminating one independent variable at a time, with constant checking and rechecking of the model by statistically using the summary output, and with every other iteration of removing an independent variable, you check for the accuracy of the model, and if you're getting a higher accuracy, you eliminate that independent variable. If not, then you simply keep it in your model. This will actually make you keep adding and deleting various independent variables of different combinations, and then finally getting to the model that you need. On the converse part of this, forward selection is basically selecting one feature at a time and including it in the model, and again testing for better accuracy. So with every iteration you add one feature, analyze the model statistically, and if it suits, you keep it, otherwise you eliminate it and add another feature, and that's how it goes on. Combining both backward and forward selection is the bidirectional comparison. Now, as the name suggests, we are doing it bidirectionally. So initially we try to go with a forward selection, we include a feature, and then with every addition of the feature in every iteration, we actually do a backward elimination at every step, and it will give you a lot of combinations of independent variables. For example, if you have 5 or 6 independent variables, you're going to actually start with selecting one feature or two feature or three feature, or a combination of 4 features and 5 features, and so it goes on. So it's very complex, but our regression model is trained in a way that it will always give better accuracy or better parameters once we actually implement a better model. So moving further, the second problem is the overfitting dilemma. Now, as we talked, overfitting is basically adding useless or huge amounts of independent variables in our data set, which actually do not improve our data set. It just increases our computational time, and basically makes your model slow in processing the data. And so we must always keep in mind that we must always try to minimize the number of independent variables. We always should try to create the best model, the most accurate model, but keeping in mind that we must do this in minimal number of independent variables. Well, if you ask me how you solve the overfitting dilemma, I would simply say common sense. But then again, common sense is not so common. So we must always try to find a way where we do a little safety checks, try to look at it in a different way, from a different angle, and then think about changing a few things, or adding a few things, and then finally get to the model. There is no precise mechanism or a particular procedure to do it, but still, if you keep a little safety in your mind, you might be able to solve it very easily. And finally, the most easiest and complex problem in this regression model, it is the dummy variable trap. Now let me explain to you what the problem is. Once you use regression for analyzing your model, what happens basically is that if you encounter a categorical variable, now what does categorical variable mean? It basically means that your data is not numerical. It might be alphabetical or alphanumeric, depending on various conditions. So if your data set is alphabetical, what you have to do is that you have to change your column. You have to change this feature or this independent variable in a way that it can be used by your regression model, because it can only evaluate numerical data sets. So what you try to do is that you count the number of unique attributes in this feature, the number of unique rows in this feature. For example, if you look at this data set, France, Germany, India, England, and I guess that's it. These are basically 4 different unique rows in this data set. So what you have to do is that you have to create a dummy variable. Now what is a dummy variable? Dummy variable is simply putting 1 where there is France and 0 everywhere else. So for example, if this row contains Germany, so Germany, as you can see, column 2, it stands for Germany. This should have 1. All the other columns should have 0. Similarly, we do this for all the rows and we get this. This is our dummy variable. Now let's not get confused by saying that for a particular row, as 1 is greater than 0 numerically, it means that France is greater than Germany or India or England in this case. It is basically just a way of attributing or representing that this column was actually a France row, that this row was actually containing the variable France as the country name. So now what happens is that when you create your dummy variables, you must always make sure to subtract 1 column out of it. So if you have a dummy variable set of n features, you must always try to remove, you must always remove 1 feature from it, because you can simply understand that if this data set, there might be rows. Suppose we are eliminating, in this data set, suppose we are eliminating England. So the places where England was actually showing the value 1 or the binary 1, in those places our row is basically displaying a 0 0 0. So once you see that there is a 0 0 0, you can automatically understand that this is basically an England column or an England row actually. So it's very easy to understand that this was England. So why need another column? Why increase the burden on our processor to... Hello and welcome to this tutorial on multiple linear regression from Analytics School Online. Unique number of inputs, create that many dummy variables and subtract 1 column from it, and here it is. You've successfully ignored the dummy variable trap, and you can move further with analyzing your data. So finally, we are done with the data pre-processing part. We've handled multi-collinearity, overfitting and dummy variable trap. We've understood how to actually deal with them. And now it's the part which is the fun part. We are going to analyze our data in Microsoft Excel. We are going to choose the method of backward elimination. You can choose other methods also, but backward elimination according to me is very simple and not that complex when you actually keep implementing models on models, including and excluding your independent variables. And we'll try with lots of parameters, with lots of combinations. So let's move forward. Let's do regression in Excel. Let's practically implement our model. It is going to be super easy, you shall trust me, I guess, and it's going to be as quick as a blink of an eye, and you just have to make sure that you are focused and you understand every small little thing. If you cannot, just look at the theoretical video again and you will understand it better. If not, you can obviously search the internet. So see you in the next video. Thank you.